Hi guys, we're ready for section 5.6, which is just more applications of exponential functions. And this is kind of one of my favorite sections because we look at some real world, some pretty cool examples of when we can use these exponential functions. And then this again is just even more practice with how to generate these exponential functions to match scenarios. Okay, so a lot of review today with just a couple of new topics. One thing I like to do in this section too is talk about that kind of almost new version of an exponential function that we haven't actually put a definition to. So we're used to, right, using the exponential function y equals c times a to the x. And this is just a slight variation of that. When we have that input variable we're given in like that half-life or that doubling time where we've learned to kind of convert the exponent in a way that allows us to use single time units rather than whatever time units that half-life or doubling time is in. So this is still the same. Again, just another variation on this function. If we still have that initial quantity c, but we're given instead that growth or decay factor in so many time units, like a doubling time in 3 days, right? Where then we would have to think about our input variable as 3-day time periods if we set it up in this function. If you've noticed that pattern of when we say, okay, let's do days, right, instead of 3-day time periods, then we can simplify down to that t, which is just the number of time units. So if I'm thinking a doubling time of 3 days, t would just simplify this equation down so that I could plug in any number of just days. Then we have that equation that y equals, or f of t in this case, okay, because we've changed it to a function of t. We still take that initial value times the growth factor, but instead of thinking of this in terms of x, which would be in terms of time periods, every time you can just think about this as changing it to that single unit. So t is in terms of days or minutes or whatever that single time unit is. We convert that to days by always just dividing by whatever that doubling time half-life or whatever growth factor in terms of so many time units we're talking about is. So if you've noticed that we always just end up dividing by that amount of time in our time periods to convert our function to be single time units for the input. Okay, so just a little bit of maybe a helpful equation there. So you can quickly now convert into, if you haven't already been doing that, quickly now convert into single time units, even if you're given a growth factor and not single time units. Okay. The other thing that's kind of helpful is we still don't know, we are going to find out in just 2 more sections, but we still don't know exactly how to find that output, right? If we're looking for a certain output, we have to just test inputs because our input variable is in the exponent. Well, one thing that's kind of helpful is if you don't know that half-life or that doubling time that you're trying to find, we have kind of a quick way to find it, so long as we have a growth or decay rate of smaller than 10%. So if we're looking at a smaller than 10% growth or decay rate, then we can get that doubling time or half-life fairly quickly by taking 70 and dividing by that rate. Now, this is the only time you will not convert a percent into the decimal form when you're using it, okay? So you use the percentage as is and take 70 divided by that percentage. And this will give you the approximate doubling time or half-life of that quantity, which we know we like to quantify exponential growth in terms of doubling time and exponential decay in terms of half-life. So I can get that approximation with a pretty simple 1-step division if instead of knowing the doubling time or half-life, I know that it decays by 7% in 3 days or something like that, okay? So that is very useful. So let's see what we can do with that to kind of help us with some of these examples and what we can do with this kind of new form stamped out for the exponential function. So we're going to do more examples today, just using those things and the stuff that we've already learned, okay? First example of some exponential growth that happens is, we've talked about this a little bit too, but there is exponential growth in the human population. And that has caused some concern for how will this affect our livelihood, right? Will we run out of resources? Something like what's going on right now with an epidemic in overpopulated areas, right? We're seeing more deaths and things like that. So we try to control that exponential growth of our population. And one thing that was done to control this growth, especially in a very overpopulated area, right? China is typically known for its overpopulation, is that in 1979, you guys have probably heard of this one-child policy. In 1979, China did introduce the one-child policy in hopes to stop this exponentially growing population that they had. Okay, so what that does, think about that in a very simplistic view. Normally, right, in our normal concept of what happens, two people get together and they would have children. So saying that those two people have two children, our population growth would stay the same. We get exponentially growing populations when every two people have more than two children because they're having more children than they are, right? So if you think about it, every two people only had one child, then we start to eventually, right, the idea would be cut our population in half by doing this. So we would stop growing because every two people would only produce one person, and we'd slow that growth down. So we have this one-child policy that was implemented. At that time in 1979, the population in China was approximately 969 million people. With the implementation of the policy, the hope was to reduce the population to 700 million by 2050. That was their goal, okay? Now what we know, last statistics, at least as far as this example goes, is that as in 2010, China's population was 1.3 billion. So clearly from implementing that policy in 1979, it's not working yet. Our population is still growing. But it has at least started to grow at a slower rate. So that means it's not exponentially growing anymore, because if our growth is exponential, that means our growth rate is continually going up. So the growth rate has slowed down, so they're not seeing exponential growth anymore, but it's still growing, all right? But what we want to investigate is, okay, so at least they've slowed it down. That growth rate that they've slowed down to was about 0.5%, okay? Pretty small growth rate, but we know that any percentage growth, right, is exponential growth, so we're still kind of worried about that if that rate even stays constant. We want that to keep going down. So let's just see what would happen. Let's see if they even have a chance of making this goal of 700 million by 2050, if we assume, okay, that it started to level off right around 1.379 billion, okay? That's what's kind of happening now. So if we assume not only has it just leveled off, but if we assume it starts to decrease, okay, and let's give it a low decay rate. Let's say that population, they can start to get it to decrease at a 0.5% per year rate. Then will they ever make it to that goal of 700 million by 2050? Okay, so we're looking at exponential decay. We're going to assume a constant percentage decrease, and a constant percent change is exponential decay. Okay, so right here, we're looking at what we're going to assume the decay rate could be. Okay, so let's get some practice with that rule of 70. Let's get an idea of what is a decay rate of 0.5%. Seems pretty small, but again, a half-life of the population would make me understand exactly how fast that's decaying a little bit better. So let's use that rule of 70. We have a percentage less than 10% to estimate the half-life of China's population at this predicted decay rate. So using that rule of 70, we check off that that rate is less than 10%, which it is. And then we just always take and divide by that actual percentage. So that's what I mean. We're not going to convert the percentage to a decimal. We're going to take 70 and divide it by 0.5. And if you do that, that's where you'll get that approximate half-life. That means the half-life of China's population is 140 years. So we would expect that current population where it's leveling off at that 1.379 to half in 140 years, approximately, by using that rule of 70 to estimate that half-life. So that is a pretty slow decay rate, right? 140 years, but half of your population, and you're looking at about, I don't know, 700 million people there. So that's a lot of people for the population to go down by. For that to only take 140 years, I mean, that's kind of up to you as to whether you think that's faster than you thought it would be or slower, okay, with that particular decay rate. But let's now explore a little bit more as to if they're going to hit that goal of getting to 700 million by 2050. So let's put this in terms of an equation now, so we can do a little bit more with this information. So I'm going to let P be my population in billions, because I'm starting with an initial population in billions, okay? So this will be my population in billions for my output. And I'm going to reinitialize my variable so that I can use this new population here. So let's do years. Whoops, that population's leveled off at that. And as far as I know, that was from last year. So we're going to do years since, and we'll just say that's today's population, years since 2020. Okay, it started to level off at that population. So let's take that population for today. Okay, so then we'd have our function, we'd have P equals our initial population, which would be that population in 2020, the population it's leveled off at, 1.379. And then we're looking for A, and hopefully that T will then be in years. So that A is going to be our decay factor per year. We're assuming a decay rate of 0.5% per year. Remember, the decay factor always equals 1 minus the decay rate. So here, we're just reasoning through all the information we've learned so far to help us find this equation. So we know the decay rate, we can always find the decay factor using that. That's 1 minus 0.005, because we will always use the decimal form there. So our decay factor would be 0.995 in this case. So if I want to know what the population is every year, be able to plug in any year I want, then I use the initial population of 1.379 billion with a decay factor of 0.995 to the T power. And that function would give me what the population, what I would estimate it to be in any year past 2020 at that assumed decay rate. Okay, so using that equation, can you then predict, and the predicted half-life, so using your equation, we have two things here, and the predicted half-life, can you determine if China will be able to reach their goal? So the other thing that the half-life does for us is it gives us a little bit of an idea of where to start guessing for this p-value. So right, our goal here is to think, okay, they want to reach their original goal. We are trying to figure out how long it'll take their population to get to 700 million. Now don't plug in 700 here, because remember our population is in billions. So if we're trying to get to 700 million and we're talking billions here, that's 0.7 billion, because 700 million is not quite a billion. So 0.7 million is what they're looking to reach in 2050. 1.379 is where they're starting right now. Right, that means 1,379,000,000 is their approximate population right now. We're taking that times 0.995, and we're trying to estimate that T value. So as I was saying, the rule of 70 gave us a half-life, right? An approximate half-life. The rule of 70 said 140 years equaled the half-life. Well, then that would mean that it approximates that we take 1.379 times a half in 140 years. So let's see how close this answer is to the output that we want. It'll give us a T value to kind of start with. That rule of 70 is helpful in helping us make an educated guess for our exponent. So if you take 1.379 times a half, you should end up with about 0.7. This is about 0.7. So then we would say, oh, that's what we're looking for here. So let's start with a good educated guess of a T value of 140 and see where we're at. Now again, the rule of 70 is an approximation, so this won't be exact, but it gives us a good place to start. So we're going to say, okay, what about t equal to 140? We're going to plug that in, 1.379 times 0.995 to the 140th power. And if you plug that into your calculator, you get about 0.684. So 140 years has gone a little too far. We're down to 684 million at that point. So then we can do a little bit of testing. We're going to say, okay, that was too far then. I went a little bit past 0.7, but obviously very close, because actually a half of 1.379 is 0.6895. So we get really close by that rule of 70, okay, to what the actual answer is. It gives us a great place to start. We're close to 0.7. So let's back up a little bit. I'm going to back up 5 years and see where we were at. Okay, again, we need to go back in time because we're decaying and we've decayed too far at 140 years. So if you plug in 135, you get about 0.701. And that's probably about as close as we're going to get. Okay, even if you plug in 136, we've gone a little too far at 0.697. So it's right there in between 135 and 136 years to get down to that population that they wanted to get to by 2050. So how long is that actually going to take them if they can possibly get to that decay rate, right, of 0.5%? Well, 135 years, that's years since 2020, right? Remember, T was years since 2020. So you need to take 2020 plus 135 years, and we would get 2,154. No, 55. Yes. See if I can do math here or not. There we go. Okay. So they're not going to reach their goal, right? They're not even decaying yet, actually. But even if they could get that to decay rate, we're already 100 years off of their goal. But we have at least slowed the exponential growth. And we can use these equations to start helping us determine, okay, then they would actually need to get to a faster decay rate and more quickly in order to ever reach that goal. So probably they've reevaluated the goal since then and come up with a new goal. But just using all that information and the stuff we've learned so far, to be able to put all that stuff together to get equations, to use the rule of 70 to help us out with some educated guesses. Okay, so population exponential growth. Another fun population exponential growth one is basically the history on where we get the idea that rabbits populations grow exponentially, and they really do. So what happened is that back in 1859, so a long time ago, there was this guy, Thomas Austin, and he collected 24 rabbits on his farm. He released 24 rabbits on his farm in Western Australia. Now, these rabbits were from a different country. I can't remember exactly where, but basically from a different environment, where the rabbit population there was not exploding because the environment itself kind of kept the population at bay. But the weather in Australia just turned out to be phenomenal for these rabbits. They just thrived on this environment in Australia. And the population started to get crazy out of control. So starting with just 24 rabbits, he was just hoping to create a population of rabbits for a hunting season, like his friends were coming in to go hunting or something like that. You can look up this story actually very easily on Wikipedia, or anywhere online. But he was just hoping to create this hunting population. Okay, what happened was it started to grow crazy fast. So in just 6 months, so in a 6-month time period, the population had already grown by 150% and continued to grow at this rate. That's a very high percentage, and we know already that any percent is exponential growth. So we can kind of see here how fast this is going to grow. Now, unfortunately, we can't use the rule of 70 here, right, to see exactly what that doubling time would be, because that percentage is certainly much greater than 10%. But we can use all the information we've learned so far to start thinking about, okay, can we generate a function to see how fast did this population grow if it did continue to grow at that 150% rate? Okay, so that means we're looking at a growth factor, sorry, we're looking at a growth rate if we have the percentage. The growth rate we're looking at is 150%. So if we're thinking about constructing an equation, we know we always need the growth factor instead of the growth rate. So remember, the growth factor always takes the growth rate plus 1. The growth rate in decimal form is 1.5. And if I add 1 to that, that means I'm going to use a growth factor of 2.5 in my equation. So we can see that the population at 150% growth rate means the population is over doubling, right? That's kind of what the percentage means compared to the factor. So I want to use t first. We're going to keep this a little bit simpler at first and say, okay, let's come up with a function for the population every 6 months. Use that original input variable, right? Because that was our growth rate every 6 months. So that means if we use every 6 months, we can just straight use the growth factor as is. We'd start with the 24 rabbits, take it times our 6-month growth factor, and that would mean we could plug in 6-month time periods. Now remember though, we had this nice easy way to change from 6-month time periods to just months. So if I actually just want to plug in months, then I think, okay, my population every month would just be this same setup, but I need to take my months and divide by the time period of the growth rate I had before. So because it was 6 months time periods, I will divide by 6 in my exponent. Okay, so a very quick way to get from a time period of 6 months and having to work with plugging that in into that single unit of months. Okay, now the one thing here though is we're going to look pretty far into the future. So what we would like to do is say, okay, is there any way I can get this to be in terms of years instead of in terms of months? So just think what you would do if you were to plug in a year. So if I was trying to plug in a year, what would I plug in for M? I would plug in 12. If I was trying to plug in 2 years, I would plug in 12 times 2 or 24. So what I'm doing is every time I want to plug in a year, I'm using this same function, but I'm just converting the months to years. So I'm going to take 12 times my however many years have passed, and that will get divided by 6 to turn months into years here. Okay, that's because if I have Y years and I want to actually change that to months, then I'm going to convert it to months so I could plug it into my previous function. That's 12 months every 1 year. So if I want to plug in months, 12y equals a month, right? So I substitute the months there for that 12y. And I keep the divided by 6 because I still need that divided by 6 in my months equation. So simplifying that, right, because 12 divided by 6 simplifies, I get that, okay, I have a new function for years by doing this other conversion. 24 times 2.5, the 2y, since 12 divided by 6 is 2. And now I have another function. I can manipulate that input variable again. So I have one function I could plug in some number of months and one function I could plug in some number of years very quickly to figure out what would happen. So use that years function to just see what that growth rate would do. What would happen after 1 year, 2 years, 5 years, and then 10 years to this population? Just see how fast that growth would change. So if you plug in 24 in 1 year, that would be 24 times 2.5 to the second power. You will get a population of 150. In just 1 year, that population of 24 rabbits will have grown to 150. If you plug in 2 there, so you have a power of 4, you'll see in just 2 years, the population will be 938 rabbits. And what happens if you go into 5 years? 5 years later, and we'll really see that exponential growth take off. If you round to the nearest whole number, that's over 220,000 rabbits. And if you do 10 years, assuming that this population continued to grow at that rate, we'd end up with over 2 billion, not trillion, 2 billion rabbits. And the crazy part is this kind of actually did happen. So now we know that this rate continued, right? But there are some things that they tried to do. Like they did try and slow this population down because it was causing all kinds of problems. The rabbits were eating all the vegetation, so it was killing out species of other animals because there wasn't enough food. And we know populations will eventually hit kind of a carrying capacity, so it wasn't able to grow, right? Think about 2 billion rabbits. It wasn't able to grow quite that high because there was just not enough resources to support that population. But it did grow out of control. So in the 1900s is when they started to start trying to control this population because it was causing so many problems in Australia with these giant rabbit populations. So they built these fences. There was like over 1,000 miles of fence. They tried to like divide up Australia. You can look that up too. It's just crazy images. But you can obviously kind of think, okay, well, it would take you way too long to build these fences. So the rabbit population was still growing. They weren't able to get the fences up fast enough to stop the rabbit populations from spreading. So that didn't work. And on top of that, the rabbits just got smarter basically and started burrowing under the fences to get through them. In the 1920s, the population had reached 10 billion. So we aren't that far off, right? By the 1920s, we had gotten to 10 billion. Now that is, let's see, this original population was in 1959, so we're talking about 50 years, okay? So if you plug in 50 into that function, you can kind of see what it would have been if that growth rate continued. So that would be 24 times 2.5 to the 100 power. It estimates it at much more than 10 billion. So clearly that growth rate had kind of slowed down. But it was still causing all kinds of problems because we now had 10 billion rabbits we didn't have before. So they really needed to get rid of these rabbits. In 1950, they came up with a virus to kind of kill out some of these rabbits. They estimated somewhere between 90 and 99%, but then they became immune to this, to the virus, okay? So anyway, even though they knocked it down to like 99%, there were still millions of rabbits. And then in 1995, they tried to release another virus. So about 50 years later, they tried to release another virus. That killed about 90% of them, but now there's still around 200 million rabbits in Australia, and it still causes problems to this day. So we can see just how powerful this exponential growth is, from just starting with a really small amount of 24. When we have a high growth rate, it can get out of control really fast. And that's one reason why as soon as we started seeing any exponential growth in this coronavirus that's going on right now, that's why there kind of ensued a panic right away, because that can just be explosive growth that gets out of control really fast. And that's why we've implemented all these social distancing policies and things like that to try and flatten that curve. By that, they mean flatten that exponential growth. Okay, another topic I want to talk about is inflation. This is another good one for you to know too, just in real life, to see how inflation affects exponential growth and things like that. We know that bank accounts have that exponential growth with their interest rates, but it's kind of combated by this inflation rate, also a percentage growth, and actually hurts our money, hurts the buying power of our money. So the one thing that's interesting about inflation, and I kind of want to get this down here in the best words that I can, is that when we talk about inflation, inflation is always given as a growth rate. Okay, we have a typical inflation of around 2 to 2.5%. So that by that they mean that money, like if I had $100, it would now be $102.5 in a year at a growth rate of 2.5%. But that doesn't mean my money is now worth $102.5. What it means is that something that cost $100 today, because the inflation rate is 2.5, will cost $102.50 in a year. So inflation is given as a growth rate, but it's essentially the growth rate in cost. Okay, it's given as a growth rate, but it decays, it decays the buying power of your money. And this is one of the major reasons that you put money into a bank, because you want that interest rate to help you combat the inflation rate that's actually decreasing the buying power of your money. Sorry, things are going crazy over here. All right, let's get back to that. I don't know why it keeps jumping down. Sorry about that. Let's see if I can get it fixed. Okay, I think we're all right now. So inflation is given as a growth rate, but it actually decays the buying power of our money. So we want to think about changing that inflation rate to understand how do we use then that inflation rate to be an actual decay rate, even though it's given as a growth rate. This is kind of one of the more confusing examples. So we want to sort through one of these to understand that inflation rate. So we're going to suppose we have a $50,000 nest egg, okay? A nest egg is kind of a term for saving money for like retirement or something like that, right? So we've got this $50,000 and we don't put it in the bank. So we just put it, quote unquote, under our mattress and wait for, and have it there waiting for us in retirement. Now, the inflation rate, we're going to assume it's kind of that average rate that we typically see of 2.5%. So we want to know, okay, if we leave that $50,000 there for our retirement, let's say that in retirement is 20 years or 30 years down the road, what will it be worth in today's dollars? So in 20 years or in 30 years, how much could that $50,000 buy in 20 years or in 30 years if we just let it sit there? So again, that buying power is going to decrease. So let me kind of see if I can simplify this a little bit more. So if we have that rate of 2.5%, so what I was saying before, if something costs $1 today, then in 1 year, I would take that dollar times the growth rate of 1 plus the growth rate that I'm given, 1.025 would be 2.5%. And that would mean that in a year, that thing that costs $1 would cost $1.02. This would be the cost in 1 year. So what we don't want to do is treat this as a growth rate, because I don't want to know what things are going to cost. I want to know what's this going to be able to buy in today's dollars in 20 years. So it's going to go down, what I can be able to buy with that $50,000. So if we think instead about our buying power and how that's changing instead of the actual cost changing, then think about that kind of in reverse. In a year, it's going to cost 1.025. What did I take that times? What rate did I take that times to get down to $1? And if you think about it that way, you're thinking, okay, I'm going to divide by 1.025. And my decay rate, R, is actually, right, always think you're finding that percent change, but it's actually your factor. So that R that I'm looking at is 0.9756 when I divide both sides by 1.025. Or if I think about this number without rounding it, that's 1.025 to the -1 power, okay? This is the decay factor of the buying power of our money, okay? So if we think about what that decay rate would be, right? We would take 1 minus that decay factor. We would end up there with about 0.244, sorry, 0.0, there we go, or 2.44%. So our decay factor of our money, our buying power is going down at a rate of about 2.44% when we're seeing a growth rate in our cost of 2.5%. So you can see that those two percentages are not the same. So we do need to do that work to get there. But this right here will kind of tell you exactly what's happening. Essentially, we're taking that growth rate in reverse, right? This was our growth factor. If we start taking that to the negative powers to kind of almost think about it, that is going back in time, we can quickly get to that buying power equation, because we're looking right there at the buying power decay in terms of the cost growth, okay? So if I put together this function, which is going to tell me the buying power of my money, I would say y equals, I have that $50,000, and with every year, right, I need to multiply by this decay factor times 1.025, and then if I take that to the negative x instead of the positive x, I will make y equal to my buying power rather than the cost, and showing that increase in cost, where x will be the number of years that we have that buying power change of an inflation at 2.5%. So I know that every time I teach this, this one gets a little bit complicated, but again, just think about the fact that inflation decreases your buying power, and it's going to decrease it at the opposite, right, of that growth rate that we're seeing that inflation is reported in. Okay, so we have an equation there that tells us how our buying power is going to be affected after so many years. So then all we have to do is plug in x equals 20 or x equals 30 to figure out what will our buying power of 50,000 be in 20 or 30 years. So if you plug in that 20, make sure it's negative when you plug it in, you'll get a buying power out of $30,514 rounded to the nearest dollar. That means if I just leave that money alone and I have a constant inflation rate of 2.5%, that my $50,000, whatever I could buy for $50,000 now, in 20 years, I'll only be able to buy $30,000 worth of goods. Okay, basically my buying power has decreased. Okay, in 30 years, that'll go down to $23,837. Let me see if I can say that again. Obviously, you still have the $50,000 under your mattress. But let's say you could buy a $50,000 car today, obviously with that $50,000, because everything's going to continue to increase in cost over time with inflation. Now, if you take that $50,000 out from under your mattress in 20 years, you would only be able to buy a car that would have been worth $30,000 when you put the money underneath your mattress. So you're not going to be able to buy as nice of a car, even though you have the same amount of money, because that money cannot buy as much stuff because inflation has decreased your buying power. So you still have $50,000, but essentially it's like you go to the car dealership, it's 20 years later, and they're like, well, that $50,000 car now costs $70,000 or whatever it would be in 20 years. You can actually buy this car for $50,000 that would have cost you $30,000 when you put that money under your mattress. So hopefully that makes some sense. Go ahead and see if you can try this now with 7%. Okay, so see if you can quickly edit this function right here to have an inflation rate instead of 7%. So what we're doing there is our buying power is still y. We still have $50,000, and the buying power is going to decrease at the negative, right, exponent of the growth rate. That would be the growth of the cost. Okay, so again, it's just 1 plus that 7%, but add that negative into the exponent and you'll start to get that decay that would happen to your money, to the buying power of your money. Okay, now I want to look at this 7% because we have in the past in recessions and things like that, seen inflation rates go as high as 7%. And that's really dangerous because that means our buying power very quickly decreases. So see what would happen compared to that normal inflation rate to your money after 20 or 30 years if for that entire time we had an inflation rate of 7%. And you'll see after 20 years, you'll already be down to a buying power of $12,921, meaning you would have been able to buy something that cost $50,000 20 years ago, and with that same $50,000, you're only going to be able to buy about $12,000 or $13,000 worth of goods. What $13,000 worth of goods would have been 20 years ago. Crazy. 30 years of this, and your buying power of that $50,000 would be down to almost $6,500. Okay, so you still have $50,000, but essentially it can only buy at that point in time when you put that $50,000 under your mattress, something that would have cost $7,000, that's all you can buy in 30 years. Okay, so that's why you want to put your money in the bank and why you want to get good interest rates when you do that, because as you're saving money, your money is also decaying in buying power without you really even seeing that necessarily. It's kind of this invisible decay of your money. Okay, so we know we like to we know we like to quantify decay in terms of half-lives. And remember, we found that percent, that decay rate of our money back up here. Let's use that decay rate and the rule of 70, because that was, that's a rate less than 10%, to find the approximate half-life of our money at each rate to compare them. So at 2.5%, remember here that we had, for that inflation, we had that being a decay rate. We took 1 minus that decay factor, okay, to get the 0.244. Sorry, I keep reading that second zero. 0.0244, and we got that to be 2.44%. So our rule of 70 says take 70 divided by that exact percentage, and our half-life then at an inflation rate of 2.5% would be 29 years. After 29 years, we'd have about half of our money, which is exactly what we see up here, right? Remember, we looked at 20 and 30. We started with $50,000. After 30 years, we had around half of our money left, which would be 25,000. Okay, so we can see that estimate working out there. 7%, make sure you convert that to its decay rate in terms of buying power. So we're going to take 1 minus 1.07 to the negative 1. This again is your decay factor and your function, right? This is your decay factor here, 1.07 to the negative 1. 1 minus that to get to decay rate. For 1.07, that'll be about 0.0654. So we can see that 7% doesn't quite match up. It's decaying at a rate of about 6.54%. So we'll take 70 divided by 6.54, always the percentage as is with the rule of 70, and we get about 11 years there. So it'll only take 11 years versus 29 years at that higher inflation rate for our money to decay in half, for that buying power of our money to decay in half. Okay, so just another look at how to use the rule of 70 in this example, and how to make sure you are in fact using the rate that you want, right? We didn't take 70 divided by 2.5 or 70 divided by 0.07, because if we did that, that would have given us the doubling time of cost, okay? Because remember, those percentages as is are inflation growth rates, which are the inflation, the growth of the cost of items. Okay, so if we would have done that, we would have actually ended up with a doubling time of cost rather than a half-life of our buying power. Okay. All right, last example here. I know this is kind of a long one, so if you need to pause, make sure you do that, take a little break and come back. This last example is also pretty cool. So this is a good example of exponential decay. You can kind of read through this on your own, but the general idea here is that we have substances, nuclear substances. We know now that nuclear waste is bad, that it can cause cancer and stuff like that, the remnants of it. But we did not know that back in the past. So in 1943, we were producing plutonium in the US at a place called the Hanford site, which is in Washington State. And we did not understand that we had to be very careful about disposal of these radioactive materials, these nuclear materials. So a lot of it was released into the air and groundwater around this area. Now, we did not also very quickly take care of this and put policies in place to slow down this waste getting into our environment. So we slowly shut down between 1964 and 1971. Finally stopped operating almost like over 40 years later, right? This whole thing started in 1943, stopped operating in 1987, so not that long ago, okay? And we've been trying to clean it up ever since. But the problem with this is that we can't have a lot of radioactive material without seeing negative effects, and radioactive materials sometimes have really long half-lives. They're decaying at a very slow rate. One of these radioactive elements is called strontium-90, and it can cause bone cancers. And it has a half-life of about 29 years. So that's pretty long time. For half of it to go away, it takes 29 years. And the problem is that we had really high levels of this. So we tested the waters and stuff at this site and saw that we had about 18,000 units per liter of this strontium. Now this curie is a way to measure the amount of radioactive material, okay? So we're saying, just understand that that's a unit that we're measuring how much radioactive material is in the water, okay? Now, right now that doesn't really help us. We're like, okay, is that bad? Is that good? What's going on? Safe drinking water can have no more than 8 of these units per liter, okay? So that's way too much. And all we can really do is wait for this to decay away. So if we look at that half-life of 29 years, use your knowledge, right? This is a good test for you to see how well you can set up these equations and stuff like that. Use your knowledge of exponential decay to say, okay, if we know the half-life is 29 years, what will the level of strontium-90 be in 87 years? Okay, so see if you can't set that equation up. Or in this particular case, if you happen to notice, you can just use half-lives for this one. If you take 87 divided by 29, that's just 3 half-lives. Okay, so we don't even have to set up an equation for this one if you don't want to. Just take 3 half-lives later from 18,000. So it gets divided by 2 once, and 1 half-life will be down to 9,000. So we're only down to 9,000 in 29 years. 29 more years later, 2 half-lives later, and we're down to 4,500. Another 29 years later, so 87 years later, we're down to 2,250 of those units, of those picocuries or picocuries. I'm not exactly sure how to say that, okay? So that's 87 years. So in about a lifetime, we're not even close to being down as far as we need to go. So let's see how long it would take to get to that rate, to get to that amount of 8, okay? So let's see, you can either come up with the function first, that might be a little bit easier, and then also approximate that decay rate for me using the half-life, okay? So think about that. If we think about the function actually first, right? We know how to come up with that function pretty easily given the half-life. We take that 18,000 original amount, which is what you might have done already to solve number 1. We take that times a half, and in order to convert to years, we always just take years and divide by that time period of the decay factor of a half. So since we used a half, that time period was 29 years, so we'll divide by 29 in our exponent. So right there, if we're thinking about, okay, what's the decay rate? We have the decay factor sitting in our equation right there. The decay factor is 0.5 to the 1 over 29. If we figure that out, then that's about 0.9764 if we round. So to get the decay rate, we always take 1 minus the decay factor, 1 minus 0.9764, and you should get a decay rate of about 0.0236 or 2.36%. Okay, so that's what we're decaying by. That's how you can quantify half-life in terms of decay rate, okay? What we're gonna do now is say, okay, if I use that equation then, how long will it take me to get down to a level of 8? So we're gonna try and get 8 equal to 18,000 times 0.5 to the t over 29. Now we already know that 87 doesn't even get us close, so we're gonna have to go pretty far. So I'm gonna jump really far. I'm gonna say, okay, let's look around like 350, okay? You make an educated guess there. We wanna get all the way down to 8, so it's gonna take a long time. So make an educated guess and plug it in. 18,000 times 0.5 to the 350 over 29. If you do that, you get down to about 4.189. So that's too far, okay? That gets us down to way past safe levels. And I'm trying to estimate when it's gonna get down to 8, okay? So I'm gonna jump back maybe like 30 years or so, right? Because I've gone about, I need to double that essentially. So if I'm thinking about half-lives versus doubling time, I know my doubling time here or my half-life here is 30 years. So I'm going to go 30 years earlier to about 320. And if I do that, we get there about 8.581. Okay. If I could hone in on this a little bit closer, I know that I need to go a little bit further. So if you plug in like 321, well, you might get a little bit closer. Let's do that real quick. If I plug in 321 divided by 29, that's about 8.378. You do 322, right? Once you get close, then you can kind of start to get, just hone in on that number one at a time. I'm gonna go to 25. 25 was too far, 22 was not enough, 322, 323, and we're really close. That's 7.987. So I kind of skip around there and I see, okay, 323 gives me 7.9876, blah, 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 okay? So around 323 years is what it'll take for that water to be safe. Basically for it to be safe for us to go into that area without being worried about being affected by the radioactive materials. So that's why we're so worried about these radioactive materials and making sure they don't get into the air and the groundwater, because it takes so long for it to go away and there's not much else that we can do to get rid of these materials. Okay, obviously right here, a really good example of when it would have been nice and easy if we knew a good way to solve for that exponent. Remember, just 2 more sections, the last section we'll cover, we'll know how to solve for that t value exactly. Okay. So just more examples today, more real life examples, more reasoning through, given different pieces of information. So hopefully kind of today you just saw some new tactics to use to help you solve these equations. And you're gonna have more examples here in your homework to kind of work through, okay? All right, guys, email me with questions.